we talked about calculating confidence intervals around effect sizes. And the tricky issue with calculating confidence intervals around effect sizes is that our point estimate or our assumed value isn't zero, right? We're not calculating confidence intervals around an effect of zero. We're calculating a confidence interval around some effect that's not zero. And so what ends up happening is we're not working with our central t distribution. Central t distribution is sampling distribution of t statistics surrounding or assuming a null value of zero. What ends up happening though is when we're calculating our confidence intervals around effect sizes, we need to use not t distribution, we need to use a non-central t distribution. Okay? Non-central t distribution, we call it not symmetrical, it's not centered around zero. This non-central t is defined by two factors. What's our central t distribution determined by?
Degrees of freedom.
Degrees of freedom, right? Just one parameter. Only thing that determines it, degrees of freedom. Our non-central t, however, determined by non-centrality parameter or your degrees of freedom. Okay, and this non-centrality parameter, this is the point at which that non-central t is distributed around. Okay, that's that's the center point of this distribution. And what that non-centrality parameter is literally an estimate of the difference between the population mean and the assumed mean under the ML, right? So if we think about this t distribution, right? If we take this t distribution and just pretend like you could just take it and start dragging that center value one way or the next, what it's going to do is it's going to start dragging that center thing out and start skewing that t distribution one way or the other, okay? And because we know that effect sizes are a linear function of our non-centrality parameter, okay? So our non-centrality parameter is a metric of the difference between the population mean and the population mean assumed under the null, right? Which is conceptually the exact same thing as our effect size, just a different metric. What we can do is if we can get that non-centrality parameter, the upper and lower bounds of that non-centrality parameter, what we can do is back translate that into confidence intervals around our effect sizes, okay? Talked about properties of this non-central t distribution. Again, what we find is that our non-central t centered around our non-centrality parameter can take any positive or negative value. When our non-centrality parameter is zero, we just default into our central t distribution. But as we start to drag that center value, right, that to the right or to the left, what it does is ends up skewing our distribution. And so our non-central distribution we know is skewed very strongly at low degrees of freedom and less so at higher degrees of freedom. Okay, and this skew is marked, increased quite a bit with increasing non-centrality parameter. Right. So if I have an effect size K of 0.8 and effect size of 0.3, all things being held equal, which non-central t is going to be more skewed? The effect size of 0.8 or the effect size of 0.3?
The effect size of 0.8.
Mm-hmm. Why is that?
Because the distribution has been dragged.
Yeah, right. So we're assuming that all things being held equal, our effect size of 0.8 corresponds to a larger non-centrality parameter than our effect size of 0.3, right? Suggesting that non-centrality parameter is larger, right? And as our degrees of freedom start to get lower, that skew starts to increase. As the degrees of freedom start to get higher, all things being equal, our distribution becomes less skewed. However, even though for our non-central t distributions, as our degrees of freedom increase, the distribution starts to increasingly approximate our central t distribution, but this is a very gradual process, even with very small absolute value of non-centrality parameters, so corresponding to even small effects, we still have some skew even with reasonably sized degrees of freedom. Okay, and what do we talk about? Does anybody remember what's the impact of working with a non-central t distribution in terms of calculating our effect intervals. What happens with this relative to, say, calculate a confidence interval around a mean for using our central T? Yes, and
They're not symmetrical.
they're not symmetrical, right? So what we can have is the upper bound may be farther out than the lower bound, right? And so our point estimate doesn't fall directly in the middle of that, right? And so it partially makes this difficult. Rajiv did a nice job in his interpretation talking about, in his interpretation of confidence intervals, talking about, the maximum probable error and things like that. So using our, so that plus and minus there, that margin of error in his interpretations, right? And when we're interpreting our standard confidence intervals with our central T distribution, it's easy, right? We just plus or minus whatever that measurement, our margin of error is, right, above and beyond, above and below our point estimate, and then we've got our interval. For our non-central T distributions, right, for our effect sizes, we can't do that, right? We're not going to find, sometimes it'll be close, but sometimes, in certain cases, we're going to find that maybe our upper value is quite a bit larger than our lower value, and this is why that's happening. Okay. So we had talked about, in the not so recent past, calculating confidence intervals around your non-centrality parameter, incredibly difficult. It's incredibly math-intensive type of thing to do, and so what we were left with is, a handful of tables developed for certain situations and things like that. It didn't make it terribly practical, but what we have now are tools. I mean, you can get on if you're a whiz in R or SAS or something like that. You can go through and sort of, and the first time I was doing this, right, I was in R, not knowing how to use R, and like literally going through sort of like by approximation, like what if I put this value in? Okay, what if I put that value in? Like that was the literal process of doing this. But James Steiger has a wonderful little tool that makes this very, very easy. All you need to do is, with this tool, again, because our non-centrality parameter is determined by our test statistic, right? So what we can do if we want to calculate a confidence interval around a mean-based comparison, all we have to do is we need to choose, tell it that we're running a T statistic, right? We want a 95% confidence interval, then we put in our T value and our degrees of freedom, and then we hit compute stats, and what it's going to do is it's going to give you an upper and lower limit on your confidence interval, right? Upper and lower limit for your non-centrality parameter. And once you have that, everything else is crazy easy, okay? Because your upper and lower limit of your non-centrality parameter is a direct linear function of your upper and lower limit of your effect size. And so what we do to get, for a single sample test, we take our lower estimate for our effect size is our non-centrality parameter divided by the square root of our sample size. Our upper limit is the upper limit of our non-centrality parameter divided by our divided by the square root of our sample size. Independent means, same type of procedure going on here. Repeated measures, same thing as this, right? Because that's all our repeated measures is it's just a single sample t-test around the mean and change scores, okay? But note, remember, and this goes for all of these, but this is particularly relevant for our repeated measures because we're basing the upper and lower limits of our effect size around, is based on our test statistic. If we're going to calculate confidence intervals around our effect size, we have to make sure we're standardizing that effect size using the same variance estimate that was used in the calculation of the test statistic. For the most part, you get away, and people probably wouldn't notice if you say ran, well, single sample, there's only one you can use for single sample, but for independent sample, let's say you ran glasses delta as your point estimate and then calculated upper and lower, I mean, you probably wouldn't be able to tell. But technically it's not correct because what you need to be doing, so your test statistic, your t-test isn't being calculated based solely on the variability at baseline, right? what should be the point estimate if you want to calculate a confidence interval around a between samples test? So what effect size estimate should you be using? What do you think, Katie?
Hedges G.
Yeah, why hedges G?
Because that uses pooled variance.
Yeah, right. That pooled variance is what's going into the calculation of your test statistic, and so we probably need to be using the pooled variance in terms of calculating, standardizing that effect so that everything's on an even playing field, right? What about hedges unbiased G? Can we calculate a confidence interval on hedges unbiased G? No. Sampling distribution, so this is what, I mean, the issue is that for some of these effect sizes, what you get is a complex sampling distribution that's not known. Like, we don't know what the sampling distribution of Glass's delta is for what hedges unbiased G is. I don't know if you were to replicate a study 1,000 times over and calculate hedges unbiased G. I don't know what that statistic, what the distribution of that statistic would be, and so I can't calculate a confidence interval around it using this procedure. Okay, but what about our repeated measures is where we really get into trouble. What are our options for standardizing repeated measure effect? What could we use? What's that? Cohen's D. So what do we use as your standardizer there?
Using the average variance.
Okay, so we could use the average variance at time 1 and time 2, right? And that would be fine. What else could we use?
What else could we use in general?
Yeah,
Or
yeah, in
what
general.
else- Or like, well, one we could use in general, but shouldn't use for this would be Cohen's D with the baseline.
Yeah, Glass's delta, right?
Oh,
Yeah, right, and so baseline standard deviation, right? But the problem is with both of those, right? What is the variance estimate that we actually use to calculate our test statistic?
For Ross's delta.
What's that?
For Ross's delta.
No, for our test statistic, for a t-test, for a paired sample t-test, what's the variance estimate that we use in the calculation of our standard error? Do we use variance at time 1 or time 2? No, what do we use? Standard deviation of the difference score, right? Or the variance of the difference scores. That's what goes into the calculation of our test statistic. And so, if we want to calculate a point estimate around a paired sample test, we're really kind of stuck with standardizing our effect size, our point estimate, using the standard deviation of the difference scores. Now, what's our concern about using standard deviation of the difference scores as our standardizer in general? We're seeing less variance, and so what does that do to our point estimate? What's the concern, Ken?
This is like blow it up.
Yeah, it'll make it real huge, right? That's the big concern, right? Because if we look at variability at time 1 and variability at time 2, right? If we calculate Glass's delta, we're just using variability at time 2. If we use the average of the variances, we're taking kind of the functionally pooled variance across the 2 time points, right? But we know that one of the big contributors to the power of our paired sample test is that we find that the variability of change is often considerably smaller than the variability at time 1 and time 2, right? So even if people are kind of all over the place when they come in and they're all over the place when they leave, if everybody's changes is about at the same rate, the variability around that difference score is going to be a lot smaller, or can be quite a bit smaller than variability that we see at either one of the time points, right? And so what ends up happening, we have concerns in general about if we use the standard deviation of the difference scores as our standardizer, that our effect size is going to be, our estimates are going to be maybe unnecessarily large relative to if we were to use standard deviation of baseline as our standardizer, or if we were to use the average variance, okay? But this isn't always the case. Sometimes you'll find when you're going through and calculating that if you use standard deviation of the difference, standard deviation of the difference score is actually marginally or maybe reasonably larger than variability at time 1 and time 2. People are responding to whatever we're doing very differently, right? And so, again, this is one of these things that's, it's a concern, but you should recognize it as a concern, not a universal, right? And so because we know that if we want to calculate a confidence interval around a paired sample test, we have to use standard deviation of difference scores. And you'll find this out, because the first time you forget to do this, what you're going to end up with is a point estimate that doesn't, like your confidence, your upper and lower bound is over here, and your point estimate is way over here, and you'll say, wow, something's not right here, right? And remember, oh, I have to go back through and do this. But what is important to remember is that, okay, this is a concern. I want to calculate confidence interval around my paired sample effect size, so I'm stuck with standard deviation of the difference scores. Probably what we ought to do is go through and just calculate Glasses delta, or take the average of the 2 time points and see what our average variance is there, and see if it's going to make a huge difference, right? If it doesn't make a huge difference, then cool, right? You might note that, you know, in general we have concerns about this. However, in this case, it looks like it's actually not a big deal, or actually the standard deviation of my differences is actually smaller than variability at time 1 or time 2, and so this actually isn't a thing. But sometimes it might be, right? Particularly for things like any type of physiological work where you're going to get very steady and systematic changes, even though people might come in all over the place, their change is very similar, right? And so that might be a time where you might want to note the limitations of your metric, why you're using it in spite of those limitations, and then maybe provide alternative estimates of effect sizes using other stuff. Or just report your means and standard deviations for everything and let people calculate it themselves, right? If you're upset about the effect size that I calculated, then calculate your own and do that, right? Again, one of these important things, always remember to incorporate your main standard deviations when you're running through research, okay? Also, this is something, and I might take this out. It's something that you can do, but not if you want to have a happy evening. When we're running power analyses, right, what you could do is you could say, all right, this is my estimate of effect that I'm looking for. What you could do is calculate calculate a confidence interval around that point estimate of effect to say, all right, what's the lower bound of my estimated effect size? What's the upper bound of my estimated effect size? And then if you really wanted to calculate for a worst case scenario, this is the effect size that I found in the literature. What am I concerned about the effect sizes I find in the literature? They're inflated, right? In fact, you should probably expect whatever effect size you pull for your power analyses to probably be bigger than it should be, right? What you could do is you could, and this would be an incredibly rigorous approach, right? You could go through, calculate a confidence interval around the point estimate of your effect size that you want to use for your power analyses. Find your lower bound, and then see how many people you would need. Power your study for that lower bound, right? I mean, this is now what ends up happening, and then you could go through and it's not a confidence interval for power necessarily, but you could say the worst case estimate. This is the lower bound of low bound of what would be reasonable for the effect size I'm looking at. This is my point estimate for what I would do. This would be the upper end, and so this is kind of the range of people that I should be thinking about looking at, or at least recognize could be a thing. Now, the issue is you'll find that these confidence intervals around our effect sizes are quite large, okay? More so when we're using our non-central t-distribution. Confidence intervals around your effect sizes are going to be relatively imprecise. Unless you've got really, really large samples, it's not uncommon to have a lower bound of, you know, for an effective 0.05, 2.8, or something like that, right? Which could be anything from a zero effect to a massive effect, so what's the use of that? I would argue it's important to know because it gives you a realistic perspective on the precision of our estimates, right? Fine, you may be happy with that effect size of 0.5 in your sample of 20, but recognize that probably that could be anywhere from sort of a small effect in the opposite direction to a massive effect going the way that you want it to, right? And so, again, I think there's been a lot of damage done in our field about sort of people failing to recognize how imprecise our estimates are, and so at least giving you a reasonable sense for what this is. Now, this might not be useful to report in a paper, right? I'm not asking you to go out there with a cat of nine tails and just flog yourself in the public square with stuff. And if you have a relatively modest sample, right, it may not make sense to say, oh, and here's a confidence interval on my effect size running from something that's negligible to something that's ridiculously large, right? So you want to make those decisions as you're going through, but something that you should be thinking about in terms of moving forward with stuff. Okay. Yeah, Sam.
But isn't it always like better to lowball the effect size?
Well,
because
yeah.
then, I mean, if you get like a small effect size, well, if you, yeah.
From a practical standpoint, right? Like if you want to assume the worst, like this is the worst that's going to happen. You're increasing the likelihood that you'll be pleased on the back end. But if your effect size is based, that you're pulling from the literature is based on, say, one sample, the only study that's ever been published that ever does this, and they've got a relatively modest sample, I mean, it's probably not reasonable to power your study to find an effect equal to D equals 0.05 because it's just going to tell you you need 10,000 people, and that's not a reasonable thing to do, right? But if, say, for instance, you're basing your study on some meta-analytic work, and there's been lots of studies looking at, say, the relationship between PTSD and social support, and there's some of those studies that say, oh, it's correlation of 0.6, right? I might like that. Meta-analysis actually says it's much lower, right? Like 0.3-ish, right? That's probably what I should be looking at as my point estimate of my effect, what I should expect. And then what I might want to do, if it's good meta-analysis, they probably have a confidence interval around that effect size and say lower bound of that 0.3 estimate is, say, 0.22, and an upper bound is something else. 0.22 might be what I power my thing to and say, all right, what would I need in terms of how many people to detect this relation in an adequately powered sample, right? And so, in theory, yes. In practice, that's kind of a different thing, right? And so we need to work within the bounds of what's realistic. Did that help? Any other questions on this? Okay. Real quick, what we'll do, just to show you how this works, and it's not rocket science, so we're just going to do maybe one example here. But I don't know if people have this. So I've got our single sample T that we demonstrated that we did in class. If you have that, and if you don't, it's fine, because I'll go through, there's a video online that walking through this as a demonstration. But what we did, if you recall, so we were taking PTSD from a sample of motor vehicle accident survivors in our study, right? And we want to know, hey, are the people who have PTSD, who are diagnosed with PTSD, not diagnosed with PTSD, are they similar to some reference point that we found in the literature or something like that, right? And so if you recall, for our first single sample test that we did, what we did is we compared our sample with a mean. So we have people with PTSD, a mean of 62, and an N of 27, and standard deviation in our sample was 13.499, okay? And our mean under the null. And for this first one, we had said, all right, what we want to do is we want to see whether or not the people who we've said have PTSD in our sample, whether or not they're reliably, that their score on this interview is larger than the population of individuals who've been in accidents but don't have PTSD based on this reference point, okay? And so a reference point for people without PTSD was 24.7, okay? And so we went through an SPSS, calculated this, and we end up with a t-statistic of 14.358, which is massive, right? A p less than 0.001, okay? And so we would say, yeah, we have, based on these data, we have sufficient evidence to claim that for a reliable difference in PTSD scores in the population of individuals that we're pulling from who have PTSD as compared to this reference population of individuals without PTSD who've also been in motor vehicle accidents, okay? So again, that was just what we had done for this single sample test. And then what we had done is we'd said, okay, we want to calculate an effect size for this. And so here we have a difference between what we saw and our assumed mean under the null of 37.3 over only standard deviation we have 13.499 gives us an effect size of 0.76, which is massive, right? But let's say now that we want to calculate an effect size, or excuse me, a confidence interval around that effect size. What do I need to do first? I need to get my non-centrality parameter, right? So what I can do, I can go over, and I've got this saved as a shortcut on my desktop because I'm cool. You can do the same if you want. And this is just a little program, right? Very simple. But all we need to do is say, okay, I'm working with a T, and I want a 95% confidence interval that I'm trying to put together here. And so what I'm going to do then is I'm going to say my T value, 14.358, with degrees of freedom 26. Hit compute. All right. And so what I end up with is a lower bound for my non-centrality parameter of 9.981, upper bound 18.674. And what I'm going to do is I'm going to now use that to go back through and calculate my confidence intervals around my effect size. So all I need to do is what's, so someone tell me what my lower is? 9.981 over square root 27. Where do I get there? What do you got, Rajiv?
1.921.
1.921. Okay. And ID upper. What's my non-centrality parameter there? 18.674 over square root of 27 is what?
3.594.
What is it?
I got 3.594.
3.594? Okay. And so, there we go, 1.92, is that right? 3.594. 0.59. And that's all there is to it. Really easy, really simple. It's the reason this doesn't happen more often in terms of why people don't incorporate this. One, these interval estimates are often really huge, right? And so they're uncomfortably large, and so it's not fun to report them. Two, I don't think a lot of people sort of recognize how simple, particularly for these means-based statistics, it is to just run these. Again, finding these non-centrality parameters has been kind of complicated, and you kind of need to be savvy at sort of running statistical programs before in order to get this stuff. You don't anymore because of that tool and similar things like that. And then three, depending on what effect size we're talking about, sort of the procedures get increasingly complicated, and sort of there's nuances and things along those lines. We'll go through and do our best to navigate some of those things so that you can go through and put these in if you'd like. But again, getting the non-centrality parameter is the hard part. Steiger's little tool makes that easy, and then once you've got that, then you're just plugging everything back in. Okay? Any questions about this process, how we did that, anything like that?
I have a question.
Yeah.
Is there an option for this for Mac?
What's that?
Is there an option for this for Mac?
I don't know. I'm not responsible for figuring out what Macs can and can't do. I was led to believe they could do anything that a PC could do and better. So I don't know if that's not something that we've found.
Yeah, there's not. No.
Okay. So I guess talk with someone with a PC or a lab computer or something like that. So yeah, is there anything else? I'm sorry, I didn't mean to stand up here and jeer at you silly Mac users, but yeah, so I don't know. If you can find something different that works on Mac, use that. You probably could, because all Mac users are creative.
There's a lot of shit.
What's you can see my Corsi mouse going.
Hey, Mac, I don't take.
Right, lots. This is my list of grievances. Any other questions about this stuff? Okay, cool. So again, what I'll do is I've got a screencast video that goes through just examples of doing the same thing with our independent sample test and our paired sample test. I mean, you can watch that if you want or not. I mean, you should be able to figure this out pretty. I mean, because the process is fairly straightforward. So, people feeling comfortable at least with the process of going through calculating confidence intervals around our effect sizes here. Cool. All right. So, just an example, right? And so it's nice to provide an example of like actual use of this type of thing and what this might look like in an actual like applied setting, because it's easier for me to just use examples I've done and not going through literature and find someone else's stuff. Again, this is an example from a paper that I did going through, and so we were looking at inpatients treatment with diagnosis of borderline personality disorder, looking at pre to post change in across different types of measures, right? And so we've got patients with symptoms of borderline personality, and then we've got reference patients who don't have borderline personality. And so just a table put in terms of mean change, 95% confidence interval around that change, our paired sample T, right? Is our effect size here, and then the confidence interval around that effect size, right? And so this was just a situation where it just made a lot of sense to go down through, and so you can look at literally magnitude of change for each one of these different groups. Here is just the raw score, right? And so if you're very familiar with any of these measures, you say, oh, that's a big jump in that measure, or that's not a big jump in that measure, however you want to do that. right? Our test statistic, our effect size, and then the confidence interval around that effect size. Anybody who wants to replicate or check any of my numbers can do that for any one of these based on the information, based on that table, right? We also don't have to put p-values on here because those t's are all massive. That's ridiculous, right? This is another thing too, right? Like some of this, it doesn't always make sense to sort of put p-value. Like, I mean, if you got a test statistic of 21, you just, and if someone really needs a p-value for that, they can just plug in a p-value calculator that test statistic for the sample size and get whatever they want to do, right? But this is just an example of it. And I think in this case it's nice because you can say, not just, oh, there's a statistical difference or statistical reduction in symptoms. You can say, no, like, look at these effect sizes, right? We started talking about here, some argument putting together. There's a lower bound estimate of change in this sample. Even our lower bound on this limit still exceeds benchmarks for large effects to try and just bring home in terms of this interpretation what's going on and what's happening in terms of stuff. Same thing here. Okay, so these are just looking at stress induction procedure. This looks familiar. It should, because it's the same data that you worked on in the last problem set. Looking at differences here at neutral, trauma, change, effect size, confidence intervals around those effect sizes, right? So not only saying, oh, we've got a large effect, lower bound for this effect is still exceedingly above standards for a large effect versus, you know, here we've got something that looks like small to medium effect. Lower bound is falling in that low, small effect. Upper bound in that high effect, right? And so the idea being that if anybody's looking at that, this is kind of the range of effects we should be expecting if one were to go through and try and replicate some of the stuff we did in that study. Okay. Questions? All right. References for effect sizes, things we'll continue to go through, but these are all excellent source materials for going through, figuring out what's happening with calculation of these effects. It's great responsibility that you're all taking on here, and I hope you appreciate it all. Okay. Questions about power, effect sizes, anything like that? All right. So this is really, like I said before, kind of the last thing we're going to be talking about in terms of this semester. We're going to go through ANOVAs, sort of one-way ANOVAs, and then finish up with factorial ANOVA. So we're kind of, again, on the downside. These last couple of assignments with the ANOVAs are going to be, because we're well into using data sets and things like that. So sets from here on out are going to be more along the lines of this last one that you did. So just anticipate that in terms of making sure you're giving yourself enough time to work through. But the nice thing is that everything that we've done up to this point is just feeding into the same types of concepts and things that we'll get into with our ANOVA design. So today we're going to go through, talk about conceptual basis of ANOVAs, talking about partitioning variability. This is going to be a big important thing in terms of understanding what's going on and how we're determining differences when we're working with more than two groups. Talk about calculations, GLM stuff. Then we'll talk about calculating effect sizes, confidence intervals, and then the big issue is going to be follow-up tests for our ANOVA designs. Okay. So, summary. To this point, what we've done is we've run through our single sample z-test, right? This is a comparison of some single sample to a reference population with a known mean standard deviation. Great where we could get it. 99.9% of the time we can't, right? So then we transition into our single sample t-test. This is a comparison of, again, of a single sample mean to some known reference population when the population standard deviation isn't known. What we do is we substitute our sample standard deviation for an estimate of our population standard deviation. And as we go through and we do that, is we substitute our sample variability for, as an estimate of our population variability. This is when we run into our t-distribution. We talked about independent sample t-test, looking at the difference in means collected from 2 independent samples, right? Again, you can think about this in terms of what's the relation of gender to some continuous outcome, or what's the relation of any dichotomous variable to some outcome, right? We're just looking at differences in a couple of different means here on a continuous outcome, and then we've got our paired sample test looking at the analysis of the mean difference scores across 2 assessment points within a single sample. Asterisk, why do we asterisk that?
Could be a paired sample,
What's that?
could be a paired sample, like a matched pair.
Matched pair, yep, we can do matched sample, right? And then we actually do have 2 different groups, we just match them up on a bunch of stuff, right? And so that's an option there, okay? So, but what happens if we want to look at more than 2 means, right? We've got more than 2 groups that are actually relevant for our design, right? We want to look at the effect of drug A, B, C on the treatment of some sort of illness, right? If we want to run this with an independent sample t-test, we can do this. It just requires us to run 3 different tests, right? A versus B, B versus C, A versus C. We can do it, right? But it's not terribly efficient, right? And so our solution is our analysis of variance, okay? This is the procedure that we're going to be using to look at differences between 2 or more groups on a continuous outcome variable. What's nice about this is it's a more efficient than our multiple tests. Complications with type 1 error, although there's some limitations to this that we'll talk about, and greater flexibility in terms of designing our experiments, interpreting our results, right? We can just do an initial test to see if there's anything else, anything going on that we should be aware of, and then do some follow-up stuff. Okay. Basic structure. Same thing as before, only this time what we're doing is we're making inferences about mean levels across 2 or more populations, right? So we've got population 1, population 2, population 3. I don't know what the means of those populations are. That's not a knowable thing for me. But what I can do is I can draw samples from these hypothetical populations, and I can test the mean of those, hopefully to infer something about these populations from which these samples are being drawn. 2 possibilities that I can get. Is I'm going to see differences, right? It's rare that my sample means are going to be identical to one another. And so we could account for those differences in 2 different ways. One, differences in our sample means are a result of random fluctuation, right? It's just the differences that we're seeing. Population 1, 2, and 3 all have exactly the same mean, right? It's just that the means of the samples that we're pulling just happen to be different from one another because we would expect that. And what's our estimate of sort of variability around what we would pull from in a random sample of a certain size? If these were all the same, right? What would account for the differences in the mean that we would see across each one of these samples?
Standard error.
Yeah, just a standard error, right? We don't expect every single sample of 15 to be identical, right? We expect that sample of 15 to jump around to some extent. It's just our standard error, right? So these observed means could be just fluctuation of our standard error, right? Or these could reflect actual real differences in the population means that are producing differences among our samples, right? Population 1, 2, and 3 all have different samples, or at least one of them has a different sample, or excuse me, population 1, 2, and 3 all have different means, or at least one of them has a different mean. Perhaps the differences that we're seeing in these sample means is driven by a true difference in their respective population means, right? So just like before, 1, it could just be random variation, right? Or 2, it could be an effect that's attributable to a real difference in our population. Questions about this? All right, some ANOVA terminology. Factor. Okay, this is our categorically independent variable, right? Our number of factors for our one-way ANOVA. How many factors are we going to have? Say it. Just one factor. There's just one variable, right? There's one categorical independent variable that's determining our group, right? So we have experimental condition, right? Experimental condition, maybe we have 3 levels, 1, 2, 3. You're in high school, 4 levels to that. We got freshman, sophomore, junior, senior, ethnicity, however we want to break that down in terms of our different categorical variables. This is our factor, okay? Level, these are the individual conditions or categories within a factor, right? So we've got 3 levels to my experimental condition factor. We've got 4 levels to high school. In this study, we have 4 levels to racial ethnic background, right? So these, we've got our factors, and then we've got our levels. Our one-way ANOVA, we're just going to be looking at the relation of a single factor with a continuous dependent variable, right? And again, we can say, are there differences, are there mean differences in outcome across condition 1, 2, or 3? Or we can just say, is condition related to outcome, right? Either one of those things are interchangeable. We often, with our means-based tests, think about things in terms of, does condition 1, 2, and 3, do they have different means? It's oftentimes more efficient just to say, is condition related to our outcome variable? Same type of thing, okay? What we're doing with our one-way ANOVA, looking at whether there are statistically reliable differences in outcome across different levels of our independent variable. Questions? All right. So, why don't we just use a bunch of t-tests, right? Why don't we just t-test the hell out of everything and then just call it good? Why do we need a whole nother analysis here? Big issue, and the main issue for use of ANOVA models, people will cite risk of type 1 error, okay? Remember that we set our type 1 error based on our alpha level. Alpha level is usually 0.05, just because that's what we use, not a real good reason for it, it's just kind of what we've always done. And so we're kind of stuck with it. But what ends up happening is that if I take a look and I want to look at mean differences on a factor with 3 levels, it's going to require 3 different independent sample t-tests. I'm going to have to test 1 versus 2, 2 versus 3, 1 versus 3. If I want to look at these in a pairwise setting, there's 3 different tests that I have to go through and take a look at, right? But what happens is our risk of type 1 error accumulates additively with, well, not additively, but accumulates with each test that we're running, okay? Across these 3 comparisons, the likelihood of our type 1 error starts to approach C times alpha, where C is the number of independent comparisons. So instead of, for this group of tests, even though we're testing each one of these individually at alpha equal 0.05, our type 1 error is 0.05 or 0.05 for each one of these. Across the 3 independent, the 3 tests looked at individually, our alpha is actually 0.15 here, right? So, assuming that the null is true, the likelihood of us claiming that there's an effect when there isn't one is about 0.1, but the probability is about 0.15 when we think what we're doing is keeping that alpha at 0.05, right? And so we've got alpha inflation. The likelihood of making at least one type 1 error in this group of tests is considerably higher than what we've set our individual alpha at. And this is kind of an important concept. Do anybody have questions? I mean, hopefully this is a review of undergraduate statistics or this concept of alpha inflation. People see what's going on here? So again, think about this as, you know, the likelihood if I hit heads or tails, right? The likelihood of me getting heads on any individual flip is 50-50, right? But if I flip that coin 5 times, the likelihood of me hitting heads on at least one of those flips is going to be considerably higher than 0.5, right? Same thing that's going on here. And so what we do with our ANOVA models is we simultaneously look at to see whether there are any differences, or we have, see if there are any differences, to see if we have evidence that would suggest a reliable difference in the means of these populations from which these samples were drawn doing this all within the same setting so as to avoid aggregate alpha inflation here, okay? Now, this in and of itself isn't a bulletproof solution. We run into problems, but we'll talk about that in a moment. Well, probably next class, to be honest, but we'll get there. All right, questions about this? All right, so our one-way ANOVA hypotheses. Setting this up a little bit tricky when we've got more than one mean, but our null hypothesis is that mean 1 equals mean 2 equals mean 3. If we want to say this in words, means from which the means from the populations from which the samples were drawn are equal, right? There's no effect of our categorical variable on outcome, right? There's no relation between, there's no effect of year in high school with GPA, right? There's no effect of experimental condition on whatever our outcome is, okay? Our null, or our alternate, I have to say make a statement of our alternative in words, because there's not a good, easy way to write this out in statistical information. Our alternate hypothesis is at least one population mean differs from the others, okay? So we would say, essentially what we would get out of our null hypotheses, we would say that these data are unlikely if the sample, or the populations from which these were drawn all have equal means. No specific alternative hypothesis in ANOVA. Why is that? Why can't I say mean 1 doesn't equal mean 2 doesn't equal mean 3? One might, right? That's not a specific, I mean, that would be one specific alternative hypothesis, right? That none of these means are equal to one another, but that doesn't capture all the potential. So we could have 2 and 3 are equal, but 1's different, 1 and 3 are different, but equal, both of these are equal to 2. Any combination that we would go through, right? So we don't have statistical notation for the alternative. We just say at least one of the population means differs from the rest. And again, this is going back to that conceptual interpretation. Basically, we're saying, again, these data would be unlikely, or what we want to assume, even though we have problems with this, is we want to conclude that data are unlikely, assuming that these the populations from which these samples are drawn have equal mean values. Okay, and so what we do is this gives us an omnibus test. Omnibus test is an overall test of significance. What it's looking at with our omnibus test, we get a statistically significant omnibus test. It's saying at least one of these means is reliably different from the rest, but doesn't tell us how these means differ, right? This is just throwing everything in there and saying, do we have evidence that something's going on, right? And what we'll do is we'll get an omnibus test. We'll look at that omnibus test and say, hey, it looks like there's something going on. It's statistically reliable, but all we can conclude is that at least one of these means differs from another, right? Now, they all might be different from all each other, but we don't know that based on the omnibus test. Omnibus test just says at least one of these things is not like the other, okay? Everybody good on this? Cool. All right, so our test statistic. Recall that if we were thinking about our t-test, conceptually what we're looking at is we've got the observed difference between two means, right? We got our observed difference. We're taking that over the top, the expected difference, if the null hypothesis is true, okay? What do we refer to the expected difference as, assuming the null hypothesis is true? Katie, what is that? What do we call the expected difference, assuming the null hypothesis is true?
Wouldn't it just be 0 difference?
What's that?
Wouldn't it just be 0 difference?
Not zero difference. What do we even call it?
Standard
Standard error, right? Just standard error, right? It's our estimate of how much, assuming that the null hypothesis is true, assuming that there's no difference, how much of a difference would we expect for two randomly drawn samples from populations with an equal mean, right? So we've just got what we observed over what we would expect to observe, assuming that there's no difference, right? Which is our standard error. And this is conceptually just this T ratio, right? And if our observed difference is enough bigger than just what we would observe just based on random sampling, then we are likely to reject the null hypothesis, right? If we don't, if the difference that we see between our two means is about what we would expect just based on sampling variability, then we would probably fail to reject, right? And not claim evidence for a reliable effect. F statistic, very similar, okay? Our F statistic that we're calculating is going to give us, we're going to take the variance between our sample means. We're going to take it over the variance expected if the null hypotheses were true. Now, what's different about our F and our T test is our F test is based on variance as opposed to mean differences, okay? And the reason for this is that it's very, very difficult to get some easy single summative number to calculate mean differences when we've got more than two groups, right? We got multiple mean differences in here, right? And so how do we do that? Well, what we do with our ANOVA model is we use variability of our scores as a measure of the magnitude of differences. And so what we're going to do is we're going to hijack variability and use this as kind of an index of how much difference we have across a set of means. Okay? So let's say I've got two different means here. Okay? We've got set 1 and we've got set 2. Okay? Set 1, mean 1 is 20, 30, 35. Set 2, we've got means of 28, 30, and 31. What we see is the variances of each one of these sets reflects the differences in means within each set. Okay? So if we have large mean differences, right, we're going to end up with large variance. If we have small mean differences, we have small variance. Okay? So if we look at here, right, we've got differences of 20, 30, 35. If we calculate the variance across these three means, we get a pretty large variance estimate here. Versus here, set 2, we've got just small differences across these means. If we calculate the variance of this set of three means, we get a small variance, right? So which one of these sets do we have, would we assume we have more difference or greater differences in? Set 1 or set 2? What do you think, Rajiv?
Set 1.
Set 1, right? How do we know this?
We have, they just calculate the difference between the means.
Okay, and so we can eyeball it and say, yeah, there's a lot of difference, but what's a more efficient metric of just eyeballing things and telling us how much a difference is that we're seeing across these means? This is variance estimate, right? This variance estimate is in and of itself an index of how much differences or the degree of differences that we have across these means. If everything's stacked right on top of one another, if all of our means of all of our groups are very similar, what's our variance going to be? Low or high? What do you think, Lauren? Low, right? We're just not going to have a lot of variability. Our means across our groups are going to all be pretty much clustered together, right? But if we've got big differences, or if at least one of those means is different, right, it's going to be hanging out for the rest. We're going to have higher variability. And so what we do is with ANOVA is we're going to try and we're going to take efforts to parcel this variability to determine presence of systematic effects. Okay, we're going to take the total variability in the set, and we're going to go through and we're going to take a look at differences and sectioning things into between treatment variance and within treatment variance. Now, treatment is just ANOVA language for a condition or a group or things along those lines, right? You can think between group differences, within group differences. But these variance estimates are what's going to make up our ANOVA model. And it's really important to understand probably what happened in your undergrad statistics course. You went over this, but didn't talk about what it actually means. And you could do that, and you could just plug things in and get F ratios, but it's going to make it really difficult to go through and follow up and apply appropriate statistics and understand what goes where and why we're using this stuff. And so if it seems like this is ridiculous that we're going through how to calculate ANOVA by hand, fair enough. It's just important to understand where these variances estimates are coming from, how they're calculated, and what they refer to, okay? So I've got, in that handout that you've got there, we've got sort of a demo example of a very small hypothetical example coming from an undergraduate textbook, but a very good undergraduate textbook, looking at a simple ANOVA problem. And what we've got here is what we're interested is the impact of temperature on learning performance, okay? And so what we've got is we've got 3 different treatments, or 3 different groups. In one group, we've got 5 people come in and they complete some sort of task in a cold room, a moderately sort of room temperature room, and then a really hot room, okay? And what we want to see is whether or not, if we freeze people out or roast them out, how the impact that has on their performance. Candace, I think you should be taking note of this, right? So if Carolyn ever has concerns with the quality of work, which she's not going to, but if she does, what we've talked about is impact of my office temperature on my performance is really, it's 40 degrees in there, I'm freezing to death. Okay, so 2 differences. Okay, there are two possible reasons for differences between our groups. We can see differences that are caused by systematic effects of whatever the treatment or group is, right? We can see differences across our means because temperature of the room really has an impact on people's performance, okay? Or, because this also plays in, we have random non-systematic differences, okay? We've got individual differences, right? Maybe people, particularly in this small sample, maybe people in sample or in the first condition are just happen to be different for some reason or another, right? Or maybe we have experimental error, right? Maybe in sample 1 we had all of our new research assistants who didn't know what they were doing and kind of screwed stuff up and entered a bunch of error in, versus treatment 2 we had someone who knew what they were doing and did it correctly, and so we were more systematic, right? And so remembering that, again, the variance that we see across or within groups can either be due to differences or random just variation per sample. Okay. So where do we see between group differences in this table here? Morgan, where do we see our between group differences?
Means?
Which means?
Between, obviously there's none between treatment 1 and 3.
Yeah.
There is between 2 and 1 and 2 and 3.
Right, so down here, right? And this is our between group differences, right? This is looking at systematic differences across our conditions. Okay. So our between group differences here, again, can be caused by systematic differences across our respective populations, or random or non-random, sort of just fuzz and error and things like that. Okay. Do you have questions? What's up? Oh yeah, they're back there.
No, sorry.
I didn't. It just freeze you out, Sam. You don't get one. Okay. So this is our between group differences. But we also have our within group differences to think about. Okay. Within each condition, right? So everybody in treatment 1, treatment 2, treatment 3, if we've conducted a good, tight experiment, okay, there should be no systematic differences within individuals of a particular category causing different scores within a group, okay? So everybody completing whatever our experimental task is, everybody completing this in treatment 1, it's the same, right? Everybody's getting the exact same thing, right? So any differences that we see in scores within a condition are a function of some random or other unmeasured factor, okay? And this is going to be our error, right? Now, it doesn't say it's all random error. It could be because of very systematic differences. It could be things that maybe I didn't account for. But if I didn't account for, if it's not a variable in my analyses, that's error, right? Now, again, if we start adding in factors and other things, then that maybe starts to shrink our error. But again, at the end of the day, if the only thing that drives performance on this task is room temperature, Lauren, what should these scores look like if the only thing that drives performance is room temperature?
If the only thing is temperature,
Yeah,
they all have the same.
it should all be the same, right? Are they all the same? And they're not, right? And so any difference, right? Any differences that we see within this group, because they've all gotten the same thing, that's error. That's error that we haven't accounted for in our equation. And this can be due to individual differences, it can be due to experimental error, it can just be due to random fuzz stuff, right? But if our measured factor is the only thing that causes differences, then everybody should be the same, and if they're not, that's just something that's attributable to just random error. So, Morgan, where do we see our within group differences in this set of data?
In individual scores,
What's that?
like differences between individual scores.
Right, right. So all of these, right? This is our these are our within group differences. So this is, even though these people are getting the exact same treatment, nothing changes. We're still seeing differences across these people, right? And so we see within group variability here. That can't be a function of systematic stuff, right? Because there's nothing systematic, at least from the perspective of our analyses, that we did to make these scores different. So we're going to chalk this up to individual differences, experimental error stuff. So going back to our F ratio, our test statistic here, going to be made up of two different types of variance: our between treatment variance and our within treatment variance. Okay? Conceptually, this is our observed group differences over the differences we would expect under the null hypotheses. Okay? Or thinking about what we had just gone through before, our observed group differences are our between treatment variance, right? So this is the variance that we see across our mean scores, made up of systematic effects and random differences, right? Over the top of our within treatment variance, right? The variances that the variability that we see within individual conditions. This is basically, we're assuming that there's scores are going to vary to some degree, right? So our within treatment variance is going to be basically the differences that we would expect if nothing's going on, or just our random differences, right? And so conceptually, if we think about this, right, our F ratio made up of between treatment variance, which is our systematic effects plus our random effects, over the top of just our random differences, what we end up with two possible scenarios, right? If we have no systematic group effects, okay, and our differences between our groups are entirely a product of just random error or systematic error, some type of error that we haven't accounted for, we have zero systematic effects, right? Basically, the populations from which these samples are drawn all have the same mean, right? So there's no true effect. And the only differences that we're seeing across our group means is a function of random effects over the top of just random variability that we would expect to see within groups, right? We're going to get an F ratio of about 1. But if the populations from which our sample are drawn do actually have real differences in their means, right? We would expect that some of that would get translated down into the samples that we're drawn from. And so we're going to get a combination of systematic effects and random effects over just our random effects that we see within our treatment variant, or from our within group stuff. These things are going to cancel out, and we're going to get an F statistic that's something greater than 1. Do people have questions? Is this clicking for people? Do people see what's going on here? Okay. So our between group variability, our between group variance is an index of differences that we see in the mean scores across our different groups, right? Do we want this to be big or large? Or excuse me. We want this to be large or small? What do we hope for, anyone? What's that? Different. Okay, so our between group variance, right? So our differences across our sample means. We want large amount of variance or small amount of variance.
Or to reject.
What's that? In order to reject or not? Large, right? We're hoping, presumably, because we're running this test, that we would expect to see large differences across our groups, right? We expect Group A to be very different than Group B, to be very different than Group C, right? And so we're gonna expect a great deal of between treatment variance because if we got, when you, in ANOVA speak, when you see variance, think difference, right? Big between group differences. And what about our within group differences? Alex, do we want to see large differences within a group or small differences? Small differences, right? Small differences suggest we've got a tight experiment. Everybody who's coming in, based on the stuff that we've accounted for, everybody's kind of scoring about the same. If people are scoring all over the place, right, that suggests that we've got quite a bit of error, right, or whatever our factor is isn't accounting for much of a difference, right? And so if we see that the differences that we see across groups are going to look like, going to be close to 1, right? And are we likely to reject or fail to reject in that scenario? Fail to reject, right? So again, kind of taking this idea of mean differences that is fairly intuitive in our t-tests and translating this over into this idea of thinking about variance as a measure of differences. Are people comfortable with this? Okay. So, our summary of our ANOVA models. We've got our total variability, right? Total variability is a full piece of the pie. This is all the variability that we have to work with within this model. And what we're going to do is we're going to take this total variability and we're going to section this off. We're going to separate it up to our between treatment variance, or the variance that we see between treatments, and our within treatment variance is just going to be our measures associated with chance, right? And the idea is our between treatments variance, right? This is stuff that's attributable to real differences in the respective populations, and also some chance error. And then we've got our within treatment variance, right? Which is just going to be stuff that's attributable just to random error stuff, right? Because everybody in the same group should be identical, right? And if they're not, that's going to be our error, okay? Now, remember that both, and this is going to be important, both our sums of squares and our variance, both measures of variability, okay? This is just different versions of the same thing. Sum of squares, variance, same thing. They're just different metrics of how much difference that we see across a set of scores, okay? Our sum of squares, remember, is the sum of the square deviation scores, where we're taking individual scores minus a mean, squaring those up and summing them up. Our variance, just the sum of squares over n minus 1. Why I want to hit back on this is because when we get into ANOVA, we're going to talk about a lot of sum of squares. Sum of squares is just a raw metric of variability, not a real interpretable one, right? Because it's not normed to anything. Variance itself doesn't have a real good interpretation of it, right? But they're just different measures of the same thing. So, when we want to go through and calculate our ANOVA model, we've got a number of different figures. The nice thing is these figures are all interrelated to one another, okay? Because it requires to calculate this, there's a lot of different figures that we're going to be calculating. Helps to set this up in a different table to organize this. What we're going to have is we're going to have between treatment effects, within treatment effects, total effects. We're going to go through and we're going to calculate standard sum of squares, degrees of freedom, and some mean squared statistics, all to get our F value here. So, for our ANOVA notation, K, this is going to be the number of levels in each factor, the number of groups or conditions, okay? How many factors do we have in a one-way ANOVA? Just one, right? So this is just our number of different groups within our one-way design. Our small n is going to be the number of scores or participants within each condition. Okay. This is nice when we've got a balanced design. What do we have when we have a balanced design, Alex? Any guesses?
You need a balanced design.
same number, right? Same number of people, right? And this oftentimes won't happen. In this simple case, we will. In the example that we have here, how many people we have in each group? 5, right? So, and it's 5. We call this a balanced design because we've got the same number of people in each group. Often this isn't the case, but as far as an introduction and calculating ANOVAs, it's a nice way to go about it because it just simplifies things. Capital N, this is our total number of scores, total number of people in the entire study. Sam, what's our total sample size in this example here?
So 5 plus 7?
Yeah.
So
15, okay. 15 people, 5 per group. T, capital T is going to be our sum of all the scores within each condition, right? This is going to be our treatment total. G is the sum of all scores in the entire study, our grand total. Questions about this? Okay, so calculating our ANOVA, and this is sort of the handout that you've got here. We go through, if we think about sum of x squared, this is sum of the squared values for all of our scores. So we've got the sum of x squares is 106, right? Basically, if we were to just square each one of these scores and add them all up, gives us this right here. Okay. G is the sum of all scores. If we add all of these values up, we get 30. Right? N, the total number of scores, 15 scores. K is the number of groups, 3 groups. Okay. People see where this is coming from? All right. And then we have group level statistics, right? T is our total, or our sum of scores within group, so 5, 25. It's just adding these up. Our sum of squares is the sum of square deviations for each group, okay? So this is the sum of squares for group 1, sum of squares for group 2, sum of squares for group 3. Our N, total number of each score, or total number of participants in each condition, 5, 5, and 5. And then here is our mean across each one of these. Questions on any of this? Okay. So, also, again, note in this example, you see variability within and between conditions, all right? Lauren, where's our between group variance? Where do we see between group variance here? Yeah, right here, right? Angela, where do we see well within group variance? Right, here we go, right? Are all these scores the same within each condition? Nope. And so what does that tell us about each one of these conditions? That we have error, right? There's something driving differences in scores aside from whatever it is that we're measuring. And if there's something driving scores that's outside of what we're measuring, what do we call that, Katie? Just error this time, right? Okay, get you all conditioned to respond to any question I ask with standard error. That's fine. I would prefer that to other questions, right? But yeah, so we've got error within each one of these, right? And what we're hoping when we run these analyses is that the variability that we see across conditions is greater than the variability that we would see within conditions, right? Because again, if each one of these populations all have an equal mean, right, then the variability that we see within groups should be about the same as the variability that we see across groups. And so if that's the case, then there's nothing to be had, right? There's nothing to be seen, we move along. But if there are true differences, if there are differences in the actual population values that are driving the differences that we see in the corresponding samples, then we should see more variability across groups than we see variability within groups. Okay. All right, so wanted to go through, and again, I can't, please don't shut off your brains and ignore this because conceptually this is going to be important, particularly when we get into thinking about calculating follow-up tests in and contrasts in this and our factorial ANOVAs, and we get into repeated measures designs. It's going to be important to understand these variance components and where they're coming from and know when to choose which ones. If we're talking about our total variability, okay? Our sum of squares total. Sum of squares total is the total variability in the entire set of scores, okay? This is all the variability across all the scores, ignoring condition, right? And so calculation of our sum of squares total conceptually, what this is the sum of squared deviations of score for individual I in group J minus the grand mean, okay? So if we take the mean of all scores in the set, and we take the deviation of every single score in the set, subtract that from the grand mean, and square those deviations, this is gonna give us our sum of squares total, okay? And so again, if we took all of the mean of everybody in the whole set, right? And then ran a deviation score of everyone's scores from the grand mean, summed those up, this would give us our sum of squares total. This is the total piece of the pie that we have to work with. This is all the variability in our data that we can go through and then split this off. And this is important to recognize because what ends up happening if we do this correctly, everything should sum to 0, and if it doesn't, we know we've made a mistake somewhere, okay? So this is your conceptual formula. This is how to think about it. In terms of calculating it, this is your shortcut, right? This is your computational formula. If you take the sum of the squared x's and subtract it over your grand total, right? Your total, and divide it it's over the number of scores in your sample. This is going to give you your sum of scores total. Okay? So again, sum of all your scores divided by your sample. So you take your total, square it over your n, right? And again, think about this as all the variability in your sample. Okay. What we're going to do is we're going to take this total variability and we're going to split this into our between group variability and our within group variability. Degrees of freedom for our sum of scores total, given as 1 less than the total number of scores. So again, these degrees of freedom for sum of scores total. How many scores do we have in this sample? Sam? And so what's our degrees of freedom total going to be? 14. Okay. So here in our table, we've got our sum of squares total equals, we'll use our computational formula here, sum of our squared x's minus our grand total squared over n. Take a look at your handout here, you can see we've got 106 minus 30 squared over 15. Degrees of freedom, 15 minus 1. Okay. And so we get, for our sum of squares total, 46 with 14 degrees of freedom. People seeing where we got this from? Okay. People understand what we're talking about in terms of total variability among a set of scores. So basically, like, think about this is just if you took all these scores, put them in a single column, and just ran the variance for all of them, this is the variance across all your scores. This is giving you the sum of squares, corresponding sum of squares for that. Okay. All right. We also then want to go through calculate our sum of squares error. Sum of squares error, this is going to be our within group variability. Okay. What we're going to do, conceptual formula, your sum of squares error is going to be the sum of the score of individual I in group J minus the mean of that condition. Okay? So what I'm going to do, if you take a look at your sheet, right, is I'm going to take, so if I'm looking at condition 1, right, I'm taking each person in condition 1, I'm taking their score, subtracting it from the group mean, squaring that, and I'm going to do the same thing for everybody in group 2 and everybody in group 3. Okay? So it's just the square of the sum of the square deviation scores of each person's score minus their respective group mean. Okay. Again, what this is giving us is how much each individual is deviating from the group mean. Because again, if we are rod end point and our factor is the only thing that drives performance within an individual group, what should be the deviation of every individual score from the group mean? Stephanie? Yeah, if our measured factor, if our grouping variable is the only thing that drives performance, should we see the deviation of any individual's, individual score from the group mean? What should that value be? If group is the only thing that determines, whatever our outcome is. Should we see any deviation from the group mean? No, right? So again, if you look at your sheet, if the only thing that drives performance in this, on this task is room temperature, what should everybody in group one, what should their scores be? All the same, right? And so if everybody's score is the same, the mean is the same as everybody's scores, no one deviates from the mean, right? And so if we have no within group error, and that's would actually be a bad thing because then it would screw up our analysis. But the idea being that your sum of squares error is just the sum of your squared deviations of everybody's score from their respective group mean, right? So we sum that up. We can also computational formula here, if we just take the sum of the squares for each group and add them up, gives us the exact same thing. Okay, and so again, this is the variability within groups due to individual differences, and so just random error and things like that that come in. Okay, our sum of squares error, this is referred to as our error term. Okay, because if there's no error, if we've perfectly captured whatever the mechanism is that drives performance, then everybody should be the same, right? And everybody should have the same score. No one should have any deviation from the mean. But we don't get that ever, right? And so what we do get is some metric of error here, right? And so our sum of squares error, we're going to refer to that as our error term, our degrees of freedom for our error term, total number of scores minus the number of levels for our factor. So, and minus k for this. Sam, you're giving me my degrees of freedom guy. How many degrees of freedom associated with our sum of squares error?
12.
Yep. Okay. So again, if we go through and we calculate this, again, computationally, it'll be easier. Sum of squares error is just the sum of our sums of squares per group. We go down through and we take a look at sum of squares for group 1, group 2, group 3, 6 plus 6 plus 4. Gives us, we've got degrees of freedom 15 minus 3. Gives us our error term of 16, degrees of freedom 12. Questions? All right. Then we've got our sum of squares treatment. Okay. Sum of squares treatment, this is the variability, this is the differences that we see across our groups. Okay. If we have a balanced design, again, a balanced design means we've got the same people, the same number of people in each group. We're going to calculate this as our cell size, our cell sample times the sum of our group mean minus the grand mean. Okay, to square that deviation score here. Okay, so again, as opposed to our sum of squares error, which is the deviation of each individual score from their respective group mean, our between group variance is going to be calculated as sum of the square deviation scores of our group mean from the grand mean. Right? Again, because Morgan, if we don't see any differences in across our groups, what should the deviation of a group mean be from the grand mean? 0, right? Because everybody's the same, everybody's identical, right? So what we're capturing here is deviations from the group mean. And if we see large deviations from the group mean, it suggests that at least some of these are varying widely. If not, it suggests that everything is the same. And so again, taking this as the square deviation of our group mean from the grand mean multiplied by the number of people we have in each cell. Right? But oftentimes, we don't end up with a balanced design. We've got cells that have different numbers of people in them. And so we just take this formula and we sort of twist it around a little bit. And then we just take our sum of squares treatment as the sum of our square deviation of each group in the grand mean multiplied by the cells, the number of people for that cell, right? So we would go, if instead of 5 people in each group we had 5, 6, and 7, we take 5 times this deviation of group 1 from the grand mean, 6 times the deviation of group 2 from the grand mean, 7 times the deviation of group 3 from the grand mean, and sum all those up. Computationally, though, we can start to work backwards. We can calculate our sum of squares treatment as the sum of squares total minus our sum of squares error. Because remember, our sum of squares total is all the variability we have in our set, and because we're just partitioning this in our one-way design into between and within, in order to get our between, we can just take our total, subtract whatever our within group variability is. All we're left with is the variability that we see between treatments. Okay. So again, sum of squares treatment, this is variability that remains after we move all our variation due to within group error, right? Once we take our total variability, right, and we suck out all the nonsense that we are seeing within group, only thing that we have left are the systematic differences that we're seeing across groups, okay? And this is going to contain our group effects as well as our conditions. Degrees of freedom for our sum squares treatment, 1 less than the number of levels in our factor. Sam, how many degrees of freedom associated with our sum squares treatment?
2.
2, perfect, right? 3 levels minus 1 gives us 2. Okay. And so again, going to our table here, our sum of squares between is our sum of squares total minus sum of squares within. We've got our total minus our within. 46 minus 16 equals 30. Degrees of freedom, 3 minus 2 equals 1. There we go. Okay. All right. Questions about calculation, sums of squares, what these variability estimates refer to. And again, sum of squares, don't be terrified by it. I was terrified by sum of squares for a long time. Like, what the hell is sum of squares? I don't even know how to think about this. All it is just a metric of variability. It's the same thing as variance. We can use it to get variance. It just, if it was saying something in a different language, just means the same thing. It's just something that might not be super interpretable to us based on where we're coming from. Okay, so we've got our sum of squares treatment. This is our differences, variability across conditions. Error is our the variability within conditions, and our total variability. This is just all the variability that we have in the set. People feel comfortable with this? This bringing you back to freshman year of college, things along those lines. I don't know when you took the stat. Maybe it wasn't freshman year of college. I don't know your life. So. All right. So we've got our sums of squares. Okay. Now we're going to go over and start talking about mean squares. Mean square. Anytime you hear mean square, this is just a variance estimate, not like kind of a variance estimate or something that approximates. Mean square is the same thing as variance. In ANOVA terms, we talk about a variance estimate as a mean squared. I don't know why, but we do, right? Mean squared just means variance, right? So you take the square root of a mean squared, what does that give you? A standard deviation. Plug that into your brain. That then just sort of make sure that you recognize that this is just, a mean squared is just a variance estimate, right? We just call it something different. I don't know why. We have to be cute and different, I guess. But so again, remember that what we're trying to do with our ANOVA model is partition things into treatment variance, between treatment variance, within treatment variance, right? And so within the context of ANOVA, our variance estimate is just referred to as a mean square. Because our mean square is just a variance estimate, all we have to do is use the original variance formula to get from our sums of squares to our mean squared. So remember that our variance is our sum of squares over degrees of freedom, right? And so nothing new or different is going on in ANOVA. We just take our sum of squares treatment over degrees of freedom. Degrees of freedom for our treatment is going to give us our mean squared error for our treatment. Same thing, our sum of squares error over degrees of freedom error is going to give our mean squared error for our variance within groups. Easy, straightforward. All we have to do, mean squared for mean squared treatment, 30 divided by 2 gives us this, 16 divided by 2 gives us this, 15, 1.3, easy to calculate and put together once we've got our mean squares. Questions on that? Okay. And then building all this up, this is just our, finally get to our F ratio, this is our omnibus test. Our F ratio is just made up of our mean squares treatment over our mean squared error, right? So basically, we're just taking the variance across our treatment groups, dividing it by the average variance within groups, and what this gives us is our F statistic. Basically, because variance is just a term for differences in ANOVA, we've got our observed group differences over the differences that we would expect, assuming that the null hypothesis is true. So again, and this is crucial, right? Because if these samples that we've all drawn, if our samples have all been drawn from populations that have identical means, all the differences that we see on average across groups should be about the same as the average differences we see within scores within a group, and we're gonna get something that's very close to 1, right? If it doesn't, if we see systematic differences across these groups, we're gonna get systematic differences plus random error over the top of random error, and we're gonna get an F statistic that exceeds 1. So our F ratio here, 15 divided by 1.33 gives us our F statistic, okay? And that was anticlimactic. I think that's all there is on this slide. Yeah. Okay. So people see how we calculated this ANOVA table for our one-way design. Questions about what any of these things mean? And again, so sums of squares and your mean squares, I mean, they're not interpretively different, right? They're just estimates of variability within and between groups. It's just different metrics. We just have to take our sum of squares to get the mean squares to calculate our F ratio, but in certain types of follow-up tests and things like that, we'll use our sums of squares directly. Okay. Questions? All right. You're calculating things. For your one-way ANOVA, everything ought to sum to 0, right? If it doesn't, you've got something problematic going on. And what this also does is we can use this to help sort of plugging different values in based on other values that we have, right? So our sum of squares treatment, sum of squares error is always going to equal your total sums of squares. Degrees of freedom treatment, degrees of freedom error, always going to equal your total degrees of freedom. Sum of squares divided by your degrees of freedom, always going to equal your mean squares. This divided by this, always going to give you your F. So you can work backwards forward from anything that goes on in this table. Questions about this? All right. So again, conceptually, just want people to be strong on understanding what we're doing and why, because we can start to feel like we're just plugging numbers into stuff and just cranking out equations because that's what we're supposed to do. But again, as we start to get into some more advanced stuff with this, we want you to know what these terms represent and where you can go through and try and optimize some of your subsequent analyses based on these designs. So again, our goal is to calculate our F ratio. This is just our variance between treatments over our variances within treatments. And again, this is ANOVA, so variance just means differences, right? Differences within, between treatments over differences within treatments. Variances within, between treatments is just our sum of squares between over degrees of freedom, same thing with our variance. This is giving us our sum of squares total between and within, degrees of freedom total between and within. Everything sums nicely and is straight with the world. We're all very happy and excited with all of this, right? I can see the intense joy that you're feeling right now, that all of this is coming together and making a lot of sense to you, right? You're like, this is what's been missing in my life. So the conceptual understanding of an ANOVA table. Okay. Questions about this or where we're getting any of this stuff from? All right. From a GLM approach, and this starts to become important when we get into like next semester's type of thing. So don't worry about this so much right now. But conceptually, if we say, right, hey, I want to know someone's value on some outcome, my best guess is just going to be everybody's mean, right? All I would do, sort of, without any additional information, if you want to know someone's GPA, right? and you don't know any other information about that person, my best guess is just the mean GPA. Whatever the mean GPA is, that's my guess. Am I very happy about that guess? Probably not. Am I gonna be right? Probably not. But across repeated tries, guessing the mean is gonna minimize the amount of differences, the amount of error that I make, right? But what we can do with our group model is if my grouping variable is related to whatever the outcome is I'm looking at, we can start to include information about that group to start refining our guess, right? Our group model is going to be a better guess than predicting the mean by adding or subtracting basically the deviation from that group from the grand mean. So let's say that I want to look at like our last example, performance, right? If I say, hey, how does someone perform on this task? I don't know, I guess I'm just gonna guess the grand mean, right? But then you say, all right, we have some additional information. Turns out I had people perform this task under different temperature conditions in the classroom, okay? And then you say, oh, that seems like that might make a difference on people's performance. And so what I'm gonna do then is I'm gonna start with the grand mean, right? And then I'm gonna add or subtract whatever the group mean is for the group of individuals performing that task under that condition, right? And this is gonna start giving me a better sense for, probably honing me in closer on an estimate for what that person's value might be if I know which group that they're in, right? So our model here, our group model is, so the score for individual I in group J is going to be the grand mean plus the grand mean, whatever the grand mean is, or excuse me, the group mean is minus the grand mean, okay? And so then basically what I've got is I'm guessing the grand mean, and then I just make an adjustment, up or down, right? Based on this, Lauren, who performed the best in our temperature example here? On average. Yeah, the people who completed in 70 degrees, right? And so what I'm gonna do is I'm just gonna take the group average, and then I'm just gonna add a couple extra points for the people who are in this mean, or in this group, versus if I'm talking about someone in completing the task in the 50-degree room and this 90-degree room, I'm gonna subtract, right, to make a downward adjustment, right? And basically what I'm functionally doing is predicting the group mean, right? Because if I take the average mean and subtract or add the deviation from the grand mean, I'm just basically predicting the group mean. People see that? So what's the grand mean here? 30 divided by 15, so the grand mean here is 2, right? So if I look at this, grand mean is 2. So if I take 2 plus, if we're talking about the 70-degree room, right, that's going to be 4 minus 2 is 2, right? So 2 is my deviation from the grand mean, but if I go down through and I take 2 plus 2 is the deviation, I'm predicting the group mean, right? The group mean here is 4, okay? And so basically, from our GLM approach, what we're just doing is we're taking, all right, we're always going to start with the mean of everybody, and then just start making adjustments based on different information that we know, right? Okay. When we get into our full structural model, what we're going to do then is go through and start adding an error term to the end of this. So what we've got is we're going to have our group mean plus an adjustment for our our grand mean, plus some adjustment for our group mean, plus some final adjustment based on the deviation of this individual from the group mean, okay? And so here we've got our grand mean, our deviation, or our specific effect of our group, and then our error term here is associated with a specific individual based on their deviation from the group mean. And if I do this, if I take for any individual and plug these values in, it's going to give me my specific observed variable there. So don't want to spend a whole lot of time on this, and you don't need to worry about this a whole lot, but just as we start to get into like GLM and regression-based models, this is what we're working with in terms of our more complicated analyses. We're just looking at some additive model where we start with the average for everybody, and then we start making adjustments up or down based on information that we know, right? I know which temperature condition you're in, and so now all of a sudden I'm just making a downward adjustment. I know that on average, people in this condition score 2 points lower than the main, or than everybody in the universe, and so I'm going to go through, and if I know Rajiv is a member of that group, I'm going to go through, for my guess for his score, I'm just going to go through, take the grand mean, and just subtract 2, right? Because I know what group he's in. Now I'm still not going to be perfect, right? Because Rajiv's not going to have the same, maybe he does have a score that's exactly equal to the group mean, probably not, right? So there's still going to be some additional stuff going on, and that's where this error term comes in. If I go through and I take Rajiv's, the deviation of Rajiv's score from his group mean score, and I substitute that in, now I've got Rajiv's actual score, right? And so this is what's going on in terms of our general linear model, and when we start talking about these as additive models, that's what this is based on. All right, I'm not going to ask you if there's questions about this because I assume there are, but we'll get to it later. Don't worry about this too much. Talk about critical values for F, distribution of our F values. Because we've got our F is a ratio of 2 different variances, F values are always positive, right? You can't have negative F values. If you get a negative F value, you can go back through and check and make sure that you haven't, you've screwed something up. Go back through and figure out where that's going on. When our null hypothesis is true, our F value is going to be centered around 1. Under the null hypothesis, this is where we're going to expect most of our values to fall. But what ends up happening as we start to get data that are increasingly unlikely, given the null hypotheses, where do our F values start to fall? Stephanie? So as our data start to get increasingly different from what we would expect under the null, what does that indicate? Are those what are our F values? What happens to our F statistics? They get increasingly large, right? And because we can't have negative F statistics, right? And they can only be large as we start to deviate from the null hypotheses, what we end up with is with a skewed distribution. Our F distribution, like our T distribution, is determined solely on our degrees of freedom. And so just like our T distribution, our F is a family of curves that are based on, with the specific distribution based on degrees of freedom. So for our example that we ran here, we had an F statistic of, what was it?
For our total F is
11.2 something, right? And so for our critical F with 2 and 12 degrees of freedom, okay, your critical value is going to be based on your degrees of freedom between and your degrees of freedom within, right? This is going to give you your critical F. We'll go through and take a look here. And here for an F critical value of 2 and 12 degrees of freedom, alpha 0.05 is 3.88, alpha 0.01 is 6.93. So where is our test statistic at? Katie? It's 11. I don't know, it's way up here somewhere, right? So would we, in this case, would we reject or fail to reject the null hypotheses based on our test statistics we've calculated? We would reject, right? Because we're picking out way out here somewhere, all right? And if you go through and take a look at that F table, you'll see that here we've got degrees of freedom in the numerator, degrees of freedom in the denominator, and then we've got different tables for if our alpha F is, if our alpha level is 0.05, 0.025, 0.01, right? What we would do is just go through to find our critical value, degrees of freedom in the numerator, denominator, go through and figure out where that value is. So, one thing to keep in mind, and this is gonna be important and it's a useful thing to know, is that our T and our F distributions are directly related to one another, okay? Specifically, for our X with 1 degree of freedom in the numerator, for our F statistic with 1 degree of freedom in the numerator is exactly equal to the square of a T distribution with whatever degrees of freedom are in the denominator, okay? We can run we can use an ANOVA to evaluate 2 groups. We don't often do it because that just seems like t-test. T-test seems like being more straightforward, but we can still run, if we have group A and group B, we can test the difference between those 2 groups using an F test, right? It's just gonna be an F with 1 degree of freedom in the numerator because our numerator degree of freedom is just our number of groups minus 1, right? But what we find is are identical to if we were to just take our T and square it, okay? So again, for 1 degree of freedom, if we took all the values in our F table for a certain degree of freedom, with 1 degree of freedom in the numerator, and took all those values, and we took, I guess, the square root of those, we would make up a T distribution. Or if we took a T degree of freedom as a certain T, all values in a T table for a certain degree of freedom, and squared those, we just get an F, okay? So if we go through, just take a look at this, if we find what's critical T value for a 2-tailed test with 20 degrees of freedom at alpha equal 0.01. So I have a T test up, a T table up. 2.845. So that's T with 20 degrees of freedom?
Yeah.
Okay. All right. What then critical value of F for degrees of freedom 1 and 20 at alpha 0.01?
Or it's 8.10.
F1 and 20. What is it, Morgan?
8.10.
8.10. Okay. All right. Someone take 2.845 and square that for me. What do you get, Alex? 8.094. Pretty close, right? And mathematically it's identical, right? It's just rounding error and table stuff, right? And so this starts to become important is because what we can do if someone reports an F statistic and we want a T statistic, because we might want a T statistic because we can transfer a T statistic into an estimate of a D, right? And this is an F run on just 2 groups, right? So it's just got 1 degree of freedom in the numerator. If you literally went through and squared all your T values for a certain degree of freedom, it would just give you an F distribution, right? So these 2 distributions are identical to one another in terms of this transform here, okay? Now, this only holds for F's with 1 degree, values of F with 1 degree and freedom in the numerator, right? But if I calculate an F for a 2-group comparison, and I want to get a T, what do I do? You just take the square root of it, right? Or if I got a T for a pairwise test and I want to translate that over to an F statistic for some reason, what do? Square, right? Back and forth, completely interchangeable. These are mathematically identical to one another. Okay. So finishing this up in terms of just a basic interpretation for the example that we went through, our null hypothesis is the mean of 50 equals the mean of 70 equals the mean of 90. Our alternative mean learning scores will differ at least 1 temperature. Actually, I need to change that. That's not, I would probably yell at myself for writing that down. It was on a thing, right? Because I want this to be stated in terms of populations, right? And I say mean learning scores in the population of individuals completing the task at 90 degrees, 70 degrees, and 50 degrees will differ, right, or something along those lines, okay? Conclusion, our F value fails within the critical region, right? Rejecting all hypotheses, conclude the mean learning scores across these populations are different, at least one temperature. Results suggest that room temperature has statistically reliable impact on learning, right? And so this piece right here, remember to do this, right? It doesn't have to be elaborate, but at the end of your conclusion, just tie everything up with a statement about, so what does this mean? What can we infer based on these data relative to the question of interest, right? This suggests that I probably shouldn't have this room at 70 or at 50 degrees or 90 degrees when we come into run our midterm, because that's going to negatively impact performance, right? You're going to do best if you have some reasonable level of temperature, right? Or bring bundled up stuff, at least to get you to where you need to be. We'll stop there. All right, thanks everyone.